We have been staring at the sky for thousands of years, and for most of that time, we were certain we understood what we were looking at. Stars, planets, darkness, a fixed, perfect, eternal ceiling above a world that sat at the center of everything. We were wrong. Not slightly wrong, not directionally wrong, completely, fundamentally, cosmically wrong. And the moment we built the instruments to finally see clearly, the moment the first real image of the universe came into focus, we realized something that should have been humbling and was instead terrifying. We had never seen the truth before. This is the story of how we learned to look. In the early 1600s, the world had an explanation for everything above the clouds. The Earth was the center. The sun moved around it. The stars were perfect, unchanging, fixed to a celestial sphere that rotated in harmony with the divine order of creation. Aristotle had said so. The Church had confirmed it, and for 1500 years, no one had seriously challenged it, because no one had the tools to look closely enough to know any different. Then, one man lifted a tube of glass to his eye. Galileo Galilei did not invent the telescope. A Dutch lens maker had assembled the basic design a year earlier. But Galileo did something more consequential than invent it. He improved it. He ground his own lenses, pushed the magnification further, made the instrument precise enough to actually reveal something. And in the winter of 1609, he pointed it at the moon. What he saw broke the old world open. The surface of the moon was not smooth, not immaculate, not the perfect sphere that centuries of philosophy had promised it would be. It had mountains, valleys, shadows cast at angles that could only mean one thing: uneven terrain. It looked with uncomfortable familiarity like the ground beneath his feet. He kept looking. Jupiter had 4 small points of light arranged around it. Night after night he watched them. They moved, they orbited. They were moons, worlds circling another world entirely, which meant that not everything in the universe revolved around the Earth. The implications were staggering. If Jupiter had its own system of orbiting bodies, if the Earth was not the unique gravitational center of all creation, then everything the Church had built its cosmology on was at risk. Galileo published. The Church responded. He was tried, forced to publicly deny what he knew to be true, and placed under house arrest for the remaining 8 years of his life. He never fully recanted in private. And the telescope, that simple arrangement of glass in a tube, continued to evolve long after he was gone, quietly accumulating knowledge generation by generation until it became something he could never have imagined. Centuries passed. The telescopes grew larger, the discoveries multiplied. But by the 20th century, astronomers had hit a wall that no amount of engineering genius could solve from the ground: the atmosphere. Earth's atmosphere is what makes this planet livable. It filters radiation, distributes heat, turns the sky the color it is. But for a telescope trying to observe the deep universe, it is a permanent, maddening obstacle. Light traveling billions of light years across space, surviving unimaginably vast distances, arrives at the edge of our atmosphere and then gets scattered, distorted, shimmered into noise by the moving columns of air it has to pass through to reach us. No ground-based telescope, no matter how large or how precisely built, could see through that interference completely. The solution, when it finally came, was audacious. Take the telescope above the atmosphere entirely. The concept had been proposed as early as the 1940s by an astronomer named Lyman Spitzer. It took 4 more decades of lobbying, of budget battles, of canceled programs and revived proposals before the funding and technology aligned. In 1990, the Hubble Space Telescope launched aboard the Space Shuttle Discovery. The expectations were enormous. This was supposed to be the sharpest eye humanity had ever turned on the universe. Scientists who had spent their careers waiting for this moment gathered around monitors and waited for the first images to arrive. And the first images were blurry. Not slightly, not in a way that could be adjusted. Fundamentally, structurally, catastrophically blurry. An investigation found the cause almost immediately, and it was almost too absurd to process. The primary mirror, a 2.4-meter disc of glass polished to an accuracy of 10 nanometers, the most precisely manufactured optical surface ever created, had been ground to the wrong shape. A single lens in the measuring device used to verify the mirror had been positioned 1.3 millimeters out of place. Because the mirror was tested against that same flawed instrument, it passed every quality check with perfect scores. It was perfectly, precisely wrong. Billions of dollars, decades of work, the most anticipated scientific instrument in history, and it could not focus. Congress was furious, the press was savage, NASA was humiliated on a global scale. But instead of giving up, they did something that had never been done before. They sent humans to fix it. In December 1993, Space Shuttle Endeavour carried 7 astronauts to Hubble's orbital altitude. 5 spacewalks, 11 days, over 35 hours of repair work conducted while moving at 17,000 miles per hour above the surface of the Earth. The fix was precise and elegant, a set of corrective optics, custom-built to counteract the exact flaw in the mirror, installed by hand in pressurized suits that reduced finger sensitivity to almost nothing. The astronauts had rehearsed in underwater training pools for months. They worked in silence and in sequence, methodically restoring what $2 billion and a 1 millimeter mistake had broken. When they were finished and the corrected images arrived on screens at the Space Telescope Science Institute, scientists who had waited years for this moment watched the stars come into sharp, perfect focus. Some of them wept. And then Hubble showed us what the universe actually looked like. The pillars of creation, towering columns of gas and dust inside the Eagle Nebula, where new stars were being born in real time. Images so striking, so visually overwhelming, that they escaped the boundaries of science entirely and became cultural objects, printed on posters, reproduced on walls in schools and offices around the world. The Hubble Deep Field. Astronomers point to the telescope at a tiny, apparently empty patch of sky, a region chosen specifically because nothing interesting was known to be there, and held the exposure for 10 consecutive days. What came back stopped the scientific world cold. Within that small dark rectangle of apparent nothingness were approximately 3,000 objects, not stars, galaxies, each containing hundreds of billions of stars, each separated from us by billions of light years. In a patch of sky that looked empty to the naked eye, there were 3,000 galaxies. The universe was not vast in the way that word is normally used. It was vast in a way that made the word itself feel inadequate, in a way that required an entirely new category of scale that human cognition was never built to process. Hubble also confirmed something that physicists had suspected but never proven. The universe is not only expanding, but accelerating. Galaxies are moving apart faster and faster, driven by something invisible and unmeasurable that fills the space between them. They called it dark energy, which is a scientific way of saying we know it exists, we can measure its effects, and we have no idea what it actually is. Hubble ran for over 30 years. It measured the age of the universe at 13.8 billion years. It watched the comet fragment and crash into Jupiter impact by impact. It photographed the birth and death of stars. It produced over 1 million observations and contributed to more than 18,000 scientific papers. By any measure, it became the most successful scientific instrument ever built. But it had a limit. It could see far. It could not see far enough. The question that Hubble kept raising and could not answer was the oldest question in cosmology. What did the universe look like at the very beginning? Not billions of years in, not even a few hundred million years in. At the moment of first light, when the first stars and galaxies ignited out of the cooling chaos that followed the Big Bang, what was there? Answering that question required a telescope that could see further back in time than Hubble could reach. Because of the way light behaves across cosmic distances, looking further into space means looking further into the past. Light travels fast, but the universe is so large that the light arriving from distant galaxies left those galaxies billions of years ago. We are not seeing what those galaxies look like now, we are seeing what they look like then. A telescope powerful enough to see galaxies 13 billion light-years away is not just an optical instrument, it is a time machine. The James Webb Space Telescope was designed to be exactly that. Its primary mirror spans 6.5 meters, nearly 3 times the diameter of Hubble's. It observes in infrared wavelengths invisible to the human eye, capable of detecting light so ancient and so stretched by the expansion of the universe that nothing else could capture it. To fit inside a rocket, it was folded, an origami of gold-coated beryllium mirrors and mechanical arms, and programmed to unfold itself in space in a sequence of 344 individual deployments. If any single one had failed, the mission was over. There was no repair option. Webb operates nearly 1 million miles from Earth, far beyond any possible human reach. It launched on Christmas Day 2021. 30 years in development, $10 billion in funding. A deployment sequence that had engineers watching in silence, checking off each step one by one, knowing that a single failure anywhere in the chain would end 3 decades of work in a moment. Everything worked. And when the first images arrived in July 2022, scientists who had spent their careers building toward this moment described what they saw as nothing they had prepared themselves for. Galaxies that should not have existed so early in the universe, already massive, already structured, already ancient, appearing in Webb's first deep fields at distances and ages that challenged models that had held for decades. Structures no one had predicted, formations that current theory struggled to explain. Once again, we had built a better eye, and once again, the universe looked different than we thought. And this is not the end. New telescopes are already being planned, already being built. Instruments more powerful than Webb, designed to push further into questions that Webb is only now beginning to raise. The extremely large telescope, currently under construction in the Chilean desert, a primary mirror 39 meters across, large enough to resolve individual stars in nearby galaxies and search the atmospheres of distant planets for chemical signatures of life. The Nancy Grace Roman Space Telescope, set to launch later this decade, designed to survey the sky 100 times faster than Hubble, mapping dark energy and searching for planets that might resemble Earth. The questions driving these instruments are the oldest ones we have. Is there life somewhere else? How exactly did the universe begin? What exists beyond the edge of what we can see? And the answer always is the same. We don't know yet. But we are building something that will help us look. Every new telescope does not simply provide answers, it generates questions that were impossible to ask before it existed. It reveals a layer of reality that was invisible until that moment, and in doing so, it shows us how much of the picture we were still missing. That has been true of every instrument, from Galileo's glass tube to the 39-meter mirror rising in the Atacama Desert today. The universe does not run out of things to show us. We just have to keep building better eyes. We began with a simple act, a person standing in the dark looking up, wondering what was there. From that, we built glass lenses and bronze tubes. Then mountaintop observatories. Then a telescope that went blind in orbit and came back to life. Then we stared at a patch of nothing and found 3,000 galaxies inside it. Then we folded a machine the size of a tennis court, sent it 1 million miles from home, and used it to look 13 billion years into the past. Each time we built a better instrument, the universe became larger than we had imagined. Each time we thought we understood the scale of things, something appeared to remind us that we were still at the beginning. That is the pattern. That has always been the pattern. We look, we see something we cannot explain, and we build a bigger lens. The sky is not a ceiling. It never was. Which corner of the universe should we explore next?